The reason twisted cables are easier to pull through a 90-degree bend or any tight spot stems from the reduction of friction. The twisting action inherent in cable construction minimizes the contact area and relative movement between the individual conductors within the cable assembly. Imagine trying to slide a stack of flat papers versus a tightly rolled tube of paper through a narrow opening. The rolled tube, analogous to a twisted cable, encounters less resistance. When conductors are untwisted, they lose this advantage. They become more prone to rubbing against each other and the interior surface of the conduit or pathway through which they are being pulled. This increased friction translates directly into a greater force required to advance the cable. Think of it as each conductor individually battling against the constraints of the bend. With a twisted cable, the conductors essentially cooperate, sharing the load and gliding more smoothly as a unit. This is not merely a theoretical concept. It is a practical observation widely recognized in the electrical trades. Seasoned electricians often employ twisting techniques, even manually twisting untwisted conductors to some extent to facilitate easier cable pulls, especially in challenging situations involving multiple bends or long runs. The principle at play is fundamental to understanding how friction affects mechanical movement. Friction is a force that opposes motion between surfaces in contact. It depends on several factors, including the materials involved, the normal force pressing the surfaces together, and the surface finish. In the case of cable pulling, the relevant surfaces are the conductors themselves, the inner wall of the conduit, and any pulling lubricant applied. By twisting the cable, the normal force, that is the force pressing the conductors against each other and the conduit wall, is distributed more evenly. This reduces the localized pressure points where friction is concentrated. Furthermore, the twisting action tends to orient the conductors in a way that minimizes their collective surface area in direct contact with the conduit wall. Consider the alternative, an untwisted bundle of conductors. In this scenario, each conductor independently presses against the conduit wall, resulting in a higher overall normal force and a greater cumulative contact area. This leads to significantly increased friction. The difference can be quite substantial, particularly in long runs or where the cable must navigate multiple bends. Pulling lubricant plays a crucial role in further reducing friction during cable installation. These lubricants are specially formulated to create a thin film between the conductors and the conduit wall, effectively minimizing the coefficient of friction. However, even with ample lubrication, the advantage of a twisted cable remains significant. The twisting action helps to distribute the lubricant more evenly, ensuring that it reaches all critical contact points. This is especially important in tight bends where the lubricant may be squeezed out under pressure. Beyond electrical wiring, this principle finds applications in various other fields. For instance, consider a rope used for climbing or towing. A twisted rope is significantly stronger and more resistant to abrasion than an untwisted bundle of fibers. The twisting action interlocks the fibers, distributing the load evenly and preventing them from unraveling under tension. Similarly, in textiles, the twisting of fibers is essential for creating strong and durable yarns. The degree of twist affects the yarn's properties such as its strength, elasticity, and texture. Even in seemingly unrelated areas, the benefits of twisting can be observed. For example, consider threading a needle. It is generally easier to thread a needle if the thread is twisted tightly at the end. The twisting action creates a pointed tip that can more easily navigate the eye of the needle. Conversely, an untwisted thread tends to fray and separate, making it difficult to pass through the eye. Returning to the specific context of electrical wiring, it is important to note that cable manufacturers carefully engineer the twist rate of cables to optimize their performance. The twist rate, measured in twists per unit length, is a critical parameter that affects the cable's flexibility, strength, and resistance to deformation. A higher twist rate generally results in a more flexible cable that is easier to bend and pull. However, excessively high twist rates can also increase the cable's susceptibility to kinking and damage. Therefore, manufacturers must strike a balance between these competing factors to achieve the desired performance characteristics. Furthermore, the National Electrical Code, or NEC, provides guidelines for the installation of cables, including requirements for bending radius and support spacing. Adhering to these guidelines is essential for ensuring the safe and reliable operation of electrical systems. Sharp bends can damage the insulation of conductors, leading to short circuits or ground faults. Similarly, inadequate support spacing can cause cables to sag and strain, potentially compromising their integrity. In summary, the ease of pulling a twisted cable compared to an untwisted one is a direct consequence of reduced friction. The twisting action minimizes contact area, distributes forces evenly, and facilitates the distribution of lubricant. This principle extends beyond electrical wiring, finding applications in various fields where friction plays a significant role. Cable manufacturers carefully engineer twist rates to optimize cable performance, and adhering to NEC guidelines is crucial for ensuring safe and reliable installations. Consider several factors that contribute to the observed difference in pulling ease. Firstly, the geometry of the conductors within the cable plays a significant role. When conductors are twisted, they tend to form a helix, effectively reducing the direct contact area between the conductors and the conduit wall. This helical arrangement also allows for a more even distribution of pulling force, minimizing localized stress points that can impede movement. Secondly, the effect of lubrication is amplified in twisted cables. Lubricants are designed to reduce friction by creating a thin film between surfaces. In a twisted cable, the lubricant is more effectively distributed along the conductor surfaces, ensuring a more consistent reduction in friction. This is particularly important in areas where the cable is subject to bending or compression. Thirdly, the mechanical properties of the cable itself contribute to the observed difference. Twisted cables tend to be more flexible and resilient compared to untwisted bundles of conductors. This increased flexibility allows the cable to conform more easily to the shape of the conduit, reducing the likelihood of snagging or binding. Furthermore, the resilience of the cable helps to absorb and dissipate pulling forces, minimizing the risk of damage. Fourthly, consider the impact of cable weight. While the weight of the cable remains constant regardless of whether it is twisted or untwisted, the distribution of that weight changes. In a twisted cable, the weight is more evenly distributed along the length of the cable, reducing the concentration of force on any single point. This can be particularly beneficial in long runs or in situations where the cable is suspended vertically. Fifthly, the method of pulling the cable can also influence the results. Proper pulling techniques, such as using a pulling eye and applying a steady, consistent force, can help to minimize friction and reduce the risk of damage. Conversely, improper pulling techniques, such as jerking or pulling at an angle, can increase friction and make the process more difficult. Sixthly, environmental factors can also play a role. Temperature, humidity, and the presence of contaminants can all affect the friction between the cable and the conduit. For example, high humidity can increase friction by causing the cable insulation to swell. Similarly, the presence of dust or debris can create abrasive surfaces that increase friction. Seventhly, consider the type of conduit being used. Different types of conduit have different surface finishes and internal diameters, which can affect the friction between the cable and the conduit wall. For example, PVC conduit tends to have a smoother surface than metal conduit, resulting in lower friction. Eighthly, the number of conductors within the cable can also influence the results. Cables with a larger number of conductors tend to be more difficult to pull, regardless of whether they are twisted or untwisted. This is because a larger number of conductors increases the overall contact area between the cable and the conduit wall. Ninthly, the size and gauge of the conductors can also affect the pulling force required. Larger conductors tend to be more rigid and less flexible, making them more difficult to bend and pull. Similarly, heavier gauge conductors tend to be more prone to sagging and binding. Tenthly, the presence of any splices or connectors within the cable run can significantly increase the pulling force required. Splices and connectors create additional friction points and can also impede the smooth passage of the cable through the conduit. The cumulative effect of all these factors determines the overall ease of pulling a cable. While twisting the cable is generally beneficial, it is important to consider all of these factors to optimize the pulling process and minimize the risk of damage. To elaborate further on the concept of friction reduction through twisting, let's consider the forces involved at a microscopic level. Firstly, adhesion refers to the attractive forces between molecules of different substances. When two surfaces are brought into contact, the molecules on each surface attract each other, creating a bond that resists movement. In the case of cable pulling, adhesion occurs between the conductor insulation and the conduit wall. By twisting the cable, the contact area between the insulation and the conduit is reduced, minimizing the adhesive forces. Secondly, cohesion refers to the attractive forces between molecules of the same substance. In the context of cable pulling, cohesion occurs within the lubricant film that separates the conductor insulation and the conduit wall. A well-formulated lubricant will have strong cohesive forces, allowing it to maintain a continuous film even under pressure. Thirdly, deformation refers to the change in shape of a material under stress. When a cable is pulled through a conduit, the conductors and insulation can deform slightly, creating additional friction. By twisting the cable, the deformation is distributed more evenly, reducing the stress on any single point. Fourthly, abrasion refers to the wearing away of a material due to friction. When a cable is pulled through a conduit, the conductors and insulation can be abraded by the rough surface of the conduit. By twisting the cable, the contact area between the cable and the conduit is reduced, minimizing abrasion. Fifthly, interlocking refers to the mechanical engagement of surface asperities. All surfaces, even those that appear smooth to the naked eye, have microscopic irregularities called asperities. When two surfaces are brought into contact, the asperities can interlock, creating a resistance to movement. By twisting the cable, the interlocking of asperities is minimized. Sixthly, electrostatic forces can also contribute to friction. When two dissimilar materials are brought into contact, electrons can transfer from one material to the other, creating an electrostatic charge. This charge can create an attractive force between the materials, increasing friction. By using appropriate materials and grounding techniques, electrostatic forces can be minimized. Seventhly, the viscoelastic properties of the materials involved can also affect friction. Viscoelastic materials exhibit both viscous and elastic behavior. When a viscoelastic material is subjected to stress, it will deform over time, and the rate of deformation depends on the viscosity of the material. In the context of cable pulling, the viscoelastic properties of the conductor insulation can affect the friction between the cable and the conduit. Eighthly, the surface energy of the materials can also play a role. Surface energy is a measure of the energy required to create a new surface. Materials with high surface energy tend to be more adhesive, while materials with low surface energy tend to be less adhesive. By using materials with low surface energy, friction can be reduced. Ninthly, the presence of surface films can also affect friction. Surface films are thin layers of material that adhere to the surface of a solid. These films can be intentionally applied, such as with a lubricant, or they can form naturally, such as with an oxide layer. The properties of the surface film can significantly affect the friction between two surfaces. Tenthly, the temperature of the materials can also influence friction. Temperature affects the viscosity of lubricants, the deformation characteristics of materials, and the adhesive forces between surfaces. By controlling the temperature, friction can be optimized.